Today we would be deriving the Ohm's law. Now, in most cases, Ohm's law is just a given. Today we would be deriving the Ohm's law and we would be using the concept of the drift velocity and the electric field, or the concept of current density, to derive the formula for Ohm's law. Now, drift velocity, we have already taken a class on this, but briefly, the drift velocity is the net velocity of the charge carriers due to the presence of electric field. So the charge carriers are largely moving randomly even in the presence of electric field, but if we add all of those random velocities together, we will find a small component of the velocity which is due to the electric field, and it is that component which we call the drift velocity. Okay, so drift velocity, note that it is that small component. Okay, so that is the first thing. Now the next thing that we would use in this derivation is the concept of relaxation time. It is denoted by the symbol tau. Okay, and the drift velocity, we would be using the symbol Vd. Some places symbol u is also given, but u is a symbol reserved for initial velocity, so we would not be using the symbol u, but we would specifically be using the symbol Vd. And the symbol tau is very standard for the relaxation time. Relaxation time is the average time between collisions of the charge carrier, that is the relaxation time. Okay, so with that information given, let us now understand the setup. What are we dealing with? What is the setup here? So here we have a battery V, and because of this battery V, the applied voltage, a electric field E, is produced in this conductor. Because of this electric field, there is a drift velocity, which is of course the experienced by the electrons present in the conductor, and the direction of the drift velocity would be opposite to the direction of the electric field because the electrons are negatively charged. Length L is the length of the conductor, A is the cross section area, and we are getting a current of I due to that drift velocity Vd through the conductor. So that is our experimental setup. Now the first thing which we have already derived, okay, so these are the formulas which we have already derived, but we would be using them here, is the formula for Vd, and we have already derived this formula on this channel. So look at the video that we have used before. So that is E, which is the electric field, E by Me multiplied by the tau, or the relaxation time. That is the formula for Vd. The next thing which we have again derived is the formula for current density, J. Okay, this Vd is vector, current density is also vector. So this formula for J also we have derived, current density J, and that is again very simple. It is E is the charge on an electron, N is the charge carrier density, electron density. Okay, and this N multiplied by Vd. That is the formula for the our current density J. Now what do we do? The first thing that we do is that we replace this Vd in the formula for J from here. Okay, so this is the what we will replace it by. So we get J, okay, is actually equal to En multiplied by E by Me tau. Okay, so this Vd we are getting from here, and we replace this Vd in here, okay, in the second formula. That is what we have done. Very simple, nothing complicated. We have not done anything complicated now. The next thing that we will do is that we know that for the conductor and the uniform electric field E is actually equal to V by I. This is something we already know. So that is what we are going to do. We are going to replace this E here, and this becomes En V by not V by I, sorry, V by L. Okay, because the electric field is uniform, therefore the electric field is equal to V, which is the voltage applied across the conductor, divided by the length L of the conductor. That is the what we are going to do here. So V by L, and then other things remain as such, E tau by Me. Now we are going to simplify this a little bit more. So what do we get? J is equal to E squared N tau by, so this is E squared N tau then we get me by L into V. Now this J is nothing but it is the current density, it is the current per unit area. So this is nothing but I by V, I by A, current density. Okay. So now to get the formula for Ohm's law, we need to find the ratio of V by I, V is to I. So what do? I bring I on this side here, okay, and I take other quantities to this side. So what do I get? V by I is equal to MEL upon, this A will remain as is, it will remain where it is, E squared and tau A. Now this, everything here on the right hand side of the formula, everything here remains constant with temperature. If the temperature does not change, the length, the area cannot really change, E cannot change, ME cannot change. So everything here would remain constant. The charge density, this is charge density N, okay, N cannot really change. All of these things will remain constant. Therefore, at a given temperature, at a particular temperature, this thing remains constant, and we give it the symbol R, which is resistance. And this is nothing, V by I is a constant, this is equal to resistance, is nothing but the formula for the Ohm's law. Okay, so again, very important derivation. It has been asked in the exams a few times, it can be asked again. Numericals based on this concept, this derivation, have been asked many times, especially this formula for current density, okay, gives us a relation between the current and the electric field, and that is very important for solving numericals. Numericals you can find on DoorstepTutor.com, physics numericals, which have used this formula several times. So definitely look at those numericals, they are fully solved, and they'll give you an idea about how to go about solving numericals based on this particular concept. Okay, thank you.